The last thing in this unit, now that we've talked about our trigonometric functions and what their graphs look like, is to look at just one example of an application of this. You will see sine and cosine functions very frequently if you take physics or different engineering classes, because anything that moves in a repetitive motion is going to be following that kind of up and down cycle that the sine and cosine graph does. So simple harmonic motion is what we're going to look at today. Sorry about that. Okay. So think about if you had a ball hanging from a string. And so if you pull the spring down and then let it go, the ball is going to bob up and down as the string, or I keep saying string, as the spring stretches down and then recoils and pulls it back up. And then gravity pulls it down and then the spring pulls it back up. So this type of up and down, or we could do back and forth oscillation, that's what oscillating means, moving back and forth, back and forth, back and forth. This is called simple harmonic motion, okay? Now, the rest position is going to be where D, the displacement, is equal to 0. So that's before you pull the ball downwards. That's called the equilibrium position. That means that the force of gravity and the force of the spring have all kind of netted out and it's at rest. So that's what this diagram over to the right is. Once we grab it and move it from that equilibrium position, then there's going to be forces acting upon it that cause the ball's distance from its equilibrium position to change over time. Now, if you look at what this looks like, you can see the path that we can trace as time goes on. This is like snapshots of the spring at each of these moments in time. At t equals 0, when we've pulled the ball all the way down, it's at the bottom there. At time equals 1, it's up a little bit more. At time equals 2, it's more close to the top. At t equals 3, it's all the way to the top. And then gravity starts to pull it back and it starts to recoil the opposite direction. And then it does it again, okay? An object that moves on a coordinate axis is in simple harmonic motion if its distance from the origin, d, at time t is given by either d equals a cosine of omega times t, that little w is the lowercase omega symbol in Greek, or d equals alpha times the sine of omega times t. The motion has amplitude, absolute value of a, just like we know it should be, and the maximum displacement of the object from its rest position. Remember, rest is where d equals 0. The rest position, if we look at this graph up above, is all this midline here. So the maximum distance from the rest position, well, that's what we've defined as amplitude in either direction, okay? The period of the motion is 2 pi divided by omega, where omega is greater than 0. This is the exact same rule as when we see our function written as y equals a times the sine of bx. It's the exact same thing. A is the amplitude, 2 pi divided by b gives you the period. But in this particular context with the physics, this formula uses omega instead of b. And so the period is the time it takes for the motion to go through one complete cycle. So number 1 says, a ball on a spring is pulled 6 inches below its rest position and then released. The period of the motion is 4 seconds. Write the equation for the ball's simple harmonic motion. This is just like the writing equation work that we did before. When we pull this ball 6 inches below its rest position, that tells us the amplitude, okay? If we kind of think about what is happening here, we're going to start down here at -6. And then it takes 4 seconds for the graph to complete one period. So this would be 4 seconds right here. Now we have to figure out what omega is equal to, or what we're used to calling b. So the rule is 2 pi divided by omega is equal to the period, which in this case is 4. So we need to solve for omega. So if we cross multiply here, think of this as over 1, we get 2 pi equals 4 times omega, and divide, we get pi halves as the value for omega. Now, The amplitude, since we're starting down at -6, amplitude is 6, but we want the value of A to be negative, and the shape of this motion looks like a cosine graph. So we would say pi halves times t. That would be our equation, and that's all there is to it. Now, there's one extra thing that we like to consider with these, and that is the frequency of an object in simple harmonic motion. So the frequency, if you look below the box there, the frequency describes the number of complete cycles per unit of time, and it's the reciprocal of the period. So if we think back to this one here, it took us 4 seconds to complete one full period. If we want to know how much of the period it covers per second, then that would be 1/4 of the period per second. That's the frequency, is 1/4. If we divide this into 4 seconds, we get 1/4 of the period, 1/4 of the period, 1/4 of the period, 1/4 of the period. That's what the frequency tells us. Instead of 4 seconds for one period, we want 1/4 of the period per second. So it's the reciprocal because we're flipping the units. So as long as you know what the period is, you just flip it over and that gives us the frequency. So here's the last example for the entire unit. Number 2, the figure shows a mass on a smooth surface attached to a spring. There's actually not a figure attached here, but we can still answer it. The mass moves in simple harmonic motion described by D equals 10 cosine pi 6t, with t measure in seconds and d in centimeters. Find the following. Okay, maximum displacement. Remember, that's the absolute value of A. So the answer here is 10. And since we're measuring D in centimeters, the maximum displacement is 10 centimeters from its original equilibrium resting position. Okay, the frequency. We need to figure out first what the period is. The period is going to be 2 pi divided by omega, which in this case is pi 6. So that's going to be really 2 pi times 6 over pi. The pi's cancel and we get 12. That's the period. And that's going to be 12 seconds. So 12 seconds for one period. The frequency is going to be the reciprocal of that. 1/12 is the frequency because that's period per how much of the period per second. So we can get through 1/12 of the period in each second. This one moves pretty slowly. And then C says, what's the time required for one cycle? Well, that is the period. So we already figured that out. It's 12 seconds. It takes 12 seconds to do one whole cycle, which means we get through 1/12 of the cycle per second. Okay. And that would be it. So this is not really anything new. It's just an application of these types of functions. And this is just one of many, many examples. If you think of the tides, like in the ocean, for example, tides come in and then tides roll out based on the moon. And then the next day they roll in and they roll out. So if we measure the height of the tide over the course of many, many days, that graph is going to look like a sine or a cosine function. Light, it travels in waves. Sound travels in waves. So the different frequencies of sounds, the different frequencies of different pigmentation waves and things like that, those are all things that we can use these trigonometric functions for. And that is where we will wrap up with our unit.